Hello and welcome back. Recall in a previous video I told you that these PV diagrams that we'll be looking at in this video are very important to exams like the MCAT or other medical exams that you take to get into specific programs like physical therapy or MD programs. So remember, the first law of thermodynamics is kind of where we're at here, and we're going to apply it to a specific problem. The change in internal energy is equal to heat added to the system minus the work done by the system. So remember, this is how we express work when we're talking about a gas. So work is equal to the integral of PDV, and this integral of PDV is just the area under the pressure versus volume graph. So we're going to apply this now to problem 15-14 from your openstax textbook, which has an accompanying figure which I've drawn on here for you. So this is pressure on the vertical, it's labeled pressure, and the units are going to be 10 to the 6th newtons per meter squared. And on the horizontal we have volume, so this is a PV diagram here. The units for the volume are 10 to the minus 3 cubic meters. And this is the process that we are shown where this is A, B, C, and D, these 4 points within the PV diagram, and you can see that the arrows are pointing in the direction that the system is moving. So the problem statement reads as the following: calculate the net work output of a heat engine following path A, B, C, D, A. So the arrow is going from A to B, and then B to C, and then C to D, and then D back to A. Now, what we want to find is the work done A to B to C to D to A. It's important to note that the change in internal energy A to B to C to D to A is 0. Why is that? Because the system returns to the original pressure and volume. It starts at A and it comes back to A. So because the pressure and the volume are the same as they were originally, then you can see that the temperature also will come back to the same temperature. Therefore, the internal energy will be the same as it was. So there will be no change in internal energy A to B to C to D to A. It's important to note. May not be of use in this particular problem, but it's good to note that. All right, so the work A to B to C to D to A can be broken up as the work from A to B plus the work from B to C plus the work from C to D plus the work from D to A. So those are all the works that we want to calculate. So the work from A to B, remember, work is just the area under the pressure versus volume graph. So from A to B, you can see I have an area underneath the curve here, which is basically this little triangle here plus this larger rectangle here. So I can write then the work from A to B as the area of this little triangle here. That's going to be 1/2 the base. The base is 4 minus 1, that length right there, which is 3.0 times 10 to the minus 3rd cubic meters, times the height, and this height right here is the difference between these two numbers, 0.6, and the units times 10 to the 6th newtons per meter squared. So that's the work, that's this piece of the work. Now I need the rest of this, which is a rectangle, so plus the area of this rectangle beneath, and that's going to be the width times the height. So the width is going to be the 3.0 times 10 to the minus 3 cubic meters times the height, and the height is 2.0 times 10 to the 6th. So 2.0 times 10 to the 6th newtons per meter squared. So that's the work from A to B. So let's go ahead and just figure out a number there. So this is going to be, you're going to have to give me a second here to get all these numbers into the calculator. And then we're going to add going to be 6,900 joules. And the change in volume is greater than 0. You can see that as the system moves from A to B, the volume is increasing from 1 to 4. Therefore, work is greater than 0 from A to B. So we'll be giving that a positive sign when we calculate our work, okay? What about the work from B to C? What is the work from B to C equal to? Well, what's the area under the curve here? There is no area under the curve. In addition, the change in volume is 0. So remember, anytime there's no change in volume, there's no work done. This is an isovolumetric process. Isovolumetric process, the work is 0. Now, there's several ways to see it, right? No area under the curve, there's no change in volume, so the work is 0. All right, so the work from C to D. All right, so the work from C to D. So the work from C to D is going to be the area under the curve from C to D. So it's going to be this area here. And you can see that that's going to amount to this little triangle here and then this rectangle below. So first of all, the little triangle. The little triangle is going to be 1/2 the base. The base is our 3.0 times 10 to the minus 3 cubic meters times the height, and the height is going to be 0.4 times 10 to the 6th newtons per meter squared. So that's the area of this little triangle, and now we need the area of this rectangle below it to get the full area. So this is going to be plus, we want the width times the height. The width is our 3.0 times 10 to the minus 3 cubic meters times the height, and the height is 0.6 times 10 to the 6th newtons per meter squared. So calculating that, we're going to have that number, and then we're going to add to it 3 to the minus 3 times 0.6 to the 6th. This is going to be 2,400. So the work, C to D, is 2,400 joules. But delta V is less than 0. As the gas or the system moves from C to D, the volume is decreasing. Therefore, the work from C to D is less than 0. So we can write the work from C to D as a minus 2,400 joules. All right. The last step now is to find out the work from D to A. So that last leg of the cycle is taking you from D to A. And you can see, again, there's no area under the curve. It's isovolumetric, so that work is 0. So now we have work A to B, work B to C, work C to D, work D to A. And when we add them all together, the work done from A to B to C to D to A is going to be the sum of our 6,900 joules, 0 joules, minus 2,400 joules, and 0 joules. And so that's going to give us 4,500 joules. And it is positive, 4,500 joules. So that's just adding those numbers together. Now, another way we could have solved this problem is we could have just found the area contained within the cycle. So notice that if I found this area that is contained A, B, C, D, back to A, this area, I would also have found 4,500 joules as the value. And you can check that yourself to ensure you get that that alternative way as well. So this gives you an idea of how to use a PV diagram and how to use the first law to extract some information. And I think we will move further with this in the next video. Thank you.